We're the University of Iowa Robotics Club. We've been working on this rover for about a year and a half now. Our team's broken down into 3 sections: mechanical, science, and systems. The wheels are equipped with composite rims, which are coupled to the motor shaft to transmit torque. Attached to each wheel via timing belts is a stepper motor, allowing for accurate rotation. On either side of the robot, the suspension system is connected through a differential bar, so when one side raises, the other side will compensate to keep the chassis level. The frame consists of 20/20 extruded aluminum. In the slots of the extrusion, plastic and composite plates were fitted with weather stripping to protect the system's devices from external debris.
Another primary focus of the mechanical team this year was the design and implementation of a robotic arm for our rover.
The task of heavy object lifting, we first started by calculating forces using 5 kilogram maximum. Then we used water jet aluminum plates on the sides using an oval shape for proper load distribution. We decided to use stepper motors as opposed to DC motors or linear actuators, as they would be more accurate and lightweight.
To be able to precisely manipulate objects during competition, we designed a stepper-driven hand with 6 degrees of freedom. With this hand, we will be able to do many tasks, including picking up small objects such as screwdrivers and flipping switches. We made use of many 3D printed parts in our design for their lightweight and for their design flexibility. A notable feature of our arm is the screw tensioning 3D printed motor mounts. These allow us to quickly and easily tighten the belts that drive the joints.
We utilize inverse kinematics in order to determine the relative position. Also, a CNN-coded in TensorFlow is used to assist this model through optical identification of the arm. These methods are correlated together in C via ROS.
For the soil retrieval process, we wanted an attachment to brush the soil, so we 3D printed brush adapters that operate on the arm. In addition to that, there will be a tube that collects the soil for onboard soil analysis.
Once a sample is collected inside of the chamber, we are able to analyze it through means of Raman spectroscopy, which looks at the variety of different bonds that can be present in the sample, as well as we are able to analyze it through use of staining methods and fluorescence that are currently used in biochemical research, such as gram staining, looking for chitin or a variety of different amino acids. And on top of all of that, we have a separate station, which is actually a weather station. It's used to measure barometric pressure, wind speed, humidity, UV light intensity, as well as temperature.
We use ROS Robotics Operating System in C, C++, and Python. Also, TensorFlow is used for machine learning. MATLAB is used to coordinate multiple sensors together.
We test our code on a miniature rover, ensuring the efficiency of our team by allowing them to work on the main rover as they need.
Our program reads in GPS coordinates and navigates to those coordinates autonomously.
It recognizes and turns to the smallest angle needed in order to reach its destination, checking and correcting as it goes.
In autonomous, the robot will determine the location of the gate through a masked RNA.
The GUI is broken down into 3 different portions: the autonomy, in which we input different coordinates into the robot, the general and specific coordinates, depending on how far along into the autonomy traversal we are. As for the science portion, we use the GUI to interact with the different instruments on the robot to get telemetry data back from the science instruments and to interact with them to use them to collect soil samples. For the teleoperational part of the GUI, we use it to get telemetry data back from the robot, as well as operate different tasks that we would not want to work with on the controller.
For communications, our rover uses ham radios with automatic frequency and encryption switching for sending over simple commands. Real-time rover control and camera feeds are fed through a Blade RF software-defined radio system built in Python.
The rover will be powered by 6 LiPo batteries in parallel at 14.8 volts. These will power the controllers for the motors. There will be 4 stepper motors and 4 DC motors. There will also be a PCB designed for power distribution for these controllers.
While the University of Iowa Robotics Club has made a lot of progress over the last year, we have a plan for the next 2 months to ensure we're able to compete at the highest level of competition. The mechanical team will manufacture the arm and implement an inverse kinematic system. The science team will combine their instrumentation with the mechanical team's chassis and arm. The systems team will work on software-defined radio for enhanced motor control, and the autonomous team will develop a pathfinding algorithm utilizing ultrasonic sensors.
We are UI Robotics.
Thanks for watching.